Welcome to a second lesson on mixture problems involving first-order differential equations. In this video, we'll focus on different inflow and outflow rates. So if we let A of t be the amount of substance dissolved in the liquid of a tank at any time t, where liquid is entering and leaving the tank, and the liquid entering the tank will have a different concentration of the substance dissolved in it. So if this is the case, we can model the change of the mixture using the differential equation dA dt equals r sub 1 minus r sub 2, where dA dt is the rate at which A of t is changing in the tank, r sub 1 is the rate at which A of t is entering the tank, and r sub 2 is the rate at which A of t is leaving the tank. To get a visual of this, we have a certain concentration being pumped into our mixing tank and then pumped out. And for our example, the inflow rate and outflow rate will be different. And because they're different, notice how the inflow rate is going to be higher than the outflow rate. The amount of liquid in the tank is going to be increasing. So we will have to consider this when setting this up. For our example, a large tank holds 300 gallons of brine solution with 40 pounds of salt. A concentration of 2 pounds per gallon is pumped in at a rate of 4 gallons per minute. The concentration leaving the tank is pumped out at a rate of 3 gallons per minute. How much salt is in the tank after 12 minutes? So we're going to start with our differential equation dA dt equals r sub 1 minus r sub 2. And we'll start by finding r sub 1 and r sub 2, where again r sub 1 is the rate at which A of t is entering the tank, and r sub 2 is the rate at which A of t is leaving the tank. Well, r sub 1 is pretty straightforward. We have 2 pounds per gallon pumped at a rate of 4 gallons per minute into the tank. So r sub 1 is going to be the product of these two. And I'm writing the units in fraction form so that we can see that the units of gallons simplifies out. So r sub 1 is going to be 8 pounds per minute. Now r sub 2 is going to be a little bit trickier because for the concentration, the amount of salt is changing, and so is the number of gallons in the tank. So for the concentration, we're going to take the amount of salt and divide by the number of gallons in the tank. So A, or A of t, is the amount of salt in the tank. Now the number of gallons is not just 300 because notice how the solution is being pumped in at 4 gallons per minute and pumped out at 3 gallons per minute. So after every minute we have 1 more gallon in the tank. So the total gallons is going to be 300 plus 1t, where t is the number of minutes. Again, because we have 1 extra gallon every minute, we have 1t here. This is going to be pounds per gallon times the rate of 3 gallons per minute. Again, gallons simplifies out. So r sub 2 is going to be 3a divided by 300 plus t, and this would be pounds per minute. So the differential equation to model this situation that we need to solve is dA dt equals r sub 1, which is 8, minus r sub 2, which I'm going to go ahead and write as 3 divided by the quantity 300 plus t times A. The reason I'm writing it this way is it's easier to recognize that this is a linear first-order differential equation. And also we know that A of 0 is equal to 40 because at time t equals 0, there's 40 pounds of salt in the tank. Now we'll go ahead and solve this using an integrating factor. So the first step will be to write this in standard form. And for a quick review, you may want to pause the video on this slide to review how to solve a linear using an integrating factor given here, where p of x is the coefficient of our function y, or in our case, the function a. So to write this in standard form, we're going to go ahead and add this quantity here to both sides of the equation. So we'd have dA dt plus 3 divided by 300 plus t times a equals 8. So here's our function p of t that we'll use to find the integrating factor. So the integrating factor, we'll call it mu of t, is going to be equal to e raised to the power of the integral of this function here, 3 divided by 300 plus t dt. So to integrate this, we go ahead and let u equal the denominator of 300 plus t. And notice that du is equal to dt. So this just ends up being e raised to the power, this would be 3 times natural log of the quantity 300 plus t. We know t is always positive, so we don't need absolute values here. And from here we can use the property of logarithms to move this 3 here to the position of our exponent. So now we have e raised to the power of natural log times the quantity 300 plus t to the third. This simplifies very nicely because we have base e here, and this is natural log or log base e. So our integrating factor is just the quantity 300 plus t raised to the third. Now we'll take this form of our differential equation and multiply everything by our integrating factor. Now remember, when we do this, the left side of this differential equation, or this side here, is equal to the derivative of the product of the integrating factor and our function a. So we can say the left side is equal to the derivative of our integrating factor, which is 300 plus t to the third, times our function a, or a of t. And we can verify this using the product rule. But if the derivative is equal to the left side of this equation, it must also equal the right side. So this is equal to 8 times the quantity 300 plus t raised to the third. And from here, we can now integrate both sides of this equation with respect to t, and then solve for our function a. So now we're going to integrate the left side and integrate the right side. Well, on the left side, the integral and derivative undo each other, so we're left with the quantity 300 plus t to the third times a. And then on the right side, if we integrate this, we would have 8 times 300 plus t to the fourth divided by 4 plus c. Notice how the 8 and the 4 simplify nicely. Let's continue this on the next slide. Now to solve for a, we'll divide by this quantity here. So on the left side, this simplifies to a, or a of t. On the right side, notice how all of this simplifies to just one factor of 300 plus t. We'll go ahead and distribute the 2. That would give us 600 plus 2t, plus here we'll go ahead and move this up into the numerator, which would change the sign of the exponent. So we'd have c times 300 plus t to the negative third. This would be the general solution to our differential equation. But remember, we also know that a of 0 is equal to 40. So this will allow us to find our constant here and find our particular solution for this differential equation. So if a of 0 is equal to 40, we'll substitute 0 for t and then set this equal to 40. So we would have 600, 2t would be 0, so we'd have 600 plus c times, this would just be 300 to the negative third power, and this equals 40. So next we would subtract 600 on both sides. That would give us negative 560. Now here we could divide by 300 to the negative third, or just multiply by 300 to the positive third. Remember, here we'd add the exponents. That would give us 300 to the 0, which is equal to 1. So we have c equals this product here, which we'll go to the calculator for. We have negative 1.512 times 10 to the 10th. Using decimal notation, we'd have negative 1512. We need 7 more zeros. So we have negative 15,120,000,000 for our constant c. which will now substitute back into our function a of t for c. So we have a of t equals 600 plus 2t minus 15,120,000,000 times 300 plus t to the negative third power. So now to answer the question, how much salt is in the tank after 12 minutes, we need to find the value of a of 12. So we'll substitute 12 for t. This would be 600 plus 24, 624 minus 15,120,000,000 times, this would be 312 to the power of negative 3. And we'll go back to the calculator. So after 12 minutes, there's approximately 126.16 pounds of salt in the tank. Now it doesn't ask, but remember, because the inflow and outflow rates are different by 1 gallon per minute, after 12 minutes it would be 312 gallons in the tank. Okay, I hope you found this helpful.